Our next presentation is instruction operand addressing on x86 platform. So in this video we're going to talk about different types of memory operands that we use in our CPU instructions. So first let's talk about what we have seen a lot already in our programs. I have already made a copy for this section of our course specific to operand addressing, and this is just an empty program with the main procedure and a single return instruction. So let's first talk about register operands. Of course, registers are like super fast global variables. They are not in memory, they are CPU resources. And when we say register addressing, it means that the memory is not accessed because the operand is contained in a register. So for example, we can use an instruction such as increment register EAX. Of course, in itself is absolutely abstract. This is just like, a resource in the CPU. We're incrementing it by 1. So there's obviously absolutely not clear what is this, why we're doing this. So of course, just a reminder that in assembly we want to write some sort of comment explaining what exactly is happening here, because it's just like using just an instruction, and register EAX is not self-explanatory. You have to explain it. Okay, so but here we're just focusing on operand addressing mode. So this is an example. I'm not going to say example. This is just register operand. Obviously, we're doing something with the register. Okay. So, and of course, some instructions can have single operands. Some instructions can have 2 operands, like add. We can say add EAX, EBX. So what we do here is just generally saying EAX equals EAX plus EBX, right? And in C programming language, you'd probably want to write it like this. I just use arithmetic assignment with the plus operation. So EAX equals EAX plus EBX. So these are examples of register operands. Next type of operand that we have seen a lot is immediate operand. So we could say also add EAX 5. So 5 is a constant encoded in the instruction itself. So let's actually build this program. And again, notice that when I loaded my project first, after making a copy, it switches to 64-bit mode. So I'd like to keep it in 32-bit mode, x86. So now I can build. And all I want is just press F11 or say debug step into to switch over to disassembly right here. And just notice that this immediate operand, what we call immediate operand, is it stored this time. This time it's just sufficient to store a single byte over here with this add instruction. So it is stored directly in the instruction encoding itself. So these are actual byte codes of the instruction that we're using right here with this add instruction. And 5 is a constant encoded in the instruction itself, and of course value 5 itself cannot be modified. It's a constant. So if I try something like this, I increment 5. Okay, so first of all, the format for such instruction doesn't even exist, but the whole idea is just ill-fated and not possible. You're trying to use constant value, and of course it's not a modifiable value, so this is not possible. And so this is the nature of the immediate operand. So here we have an example of an immediate operand. And the highlight of immediate is that, again, just like with register, an immediate operand is not accessing any memory. So it's part of the instruction, and as soon as the instruction is loaded into CPU for execution, we have it already loaded. It's already inside the CPU, so there is no any way of going out to memory and getting something from memory. Another type of addressing that we have seen in our code multiple times is called direct memory operand. So if we have some kind of value right here, so let's just make more space for our examples here. So we could create a value. It could be a double word, right? And we can initialize it to 0. So we can say add EAX value. Okay, and so this is an example of direct memory operand. So in this situation, the value is the offset in the initialized global data memory segment, right? So the value is just a label inside this initialized data segment, and it shows how far away from the beginning of the segment this thing is residing. And in the syntax, as soon as we start using square brackets, we know that this is an operand in memory. Therefore, the address has to be used to access the memory. So once again, let's just build this code and step into F11 and just take a look at the disassembly. And so right here we have this add EAX, and so in disassembly, of course, the value is shown to us as an offset in our global memory segment. And of course, what in our flat memory model that we're using when we're executing this program, this part right here, right, this entire set of instructions is residing in a text memory segment which represents the executable code. And of course we also have the data memory segment, and this is where our value is. So this of course is, and because this is flat memory model, so we also have stack memory segment here, and this is entire image of our program, and of course other operating system modules are also loaded into this memory space. But this is really in this flat memory segment, isn't this, that everything is in the same address space. It just happens that our loader, the operating system loader component, placed our value in this specific offset from the beginning of the memory segment, and of course, so this is the value located right here, and that's the address. So anyway, this format of the instruction, the add instruction, using the name of the variable, roughly, debug, stop debugging, right? So I'm talking about this memory allocation directive that we use to allocate space for an integer, set it to 0, and this is an example of a direct memory operand. So we're directly speaking, like it's just like using a variable in C programming language, right? So we can say integer x equals whatever. So that's direct access to that variable. So that's the same idea right here when we're talking about different operand addressing on 32-bit x86 Intel platform.